Great reunions. Okay. So I want to tell you about something I've been obsessing about the last 3-4 years with the help of mainly two friends, Amir Yehudayoff and Pavel Hrubes. And but this is going to be because I allowed myself to take next week also, so I will want to focus on non-commutative arithmetic computation and the questions that are still open there. Some beautiful questions. Hopefully, some of you will be attracted by them. But I'll turn it into I want to give a background to contrast what we know in the non-commutative case with what we know in the commutative case. This will be mainly about sort of the complexity theoretic structure of arithmetic computation. It will not be about, many of you know that the last few years, sort of the history of lower bounds for arithmetic circuits was rewritten. There's a great survey that was written just 3 years ago by Amir Yehudayoff and Amir Spilka, and sort of it's obsolete in some sense because, I know it's not obsolete and it's a great read, but the last few years there were beautiful results proving lower bounds on restricted models of arithmetic computation, and I'm not going to touch these at all. I'm going to talk about about general circuits, so the most powerful circuits not restricted by multilinearity or by depth, etc. Anyway, so what are arithmetic circuits? So this is going to be slow. I want everybody to understand everything, and if you are not familiar with something or my notation is not familiar to you, just ask. So what are arithmetic circuits? These are we are trying to understand what can be done with arithmetic operations. That's just plus, minus, times, and division. So even though it doesn't really need justification to study the power of the arithmetic operations, we've known them from first grade. I just want to say that from the lower bounds point of view, we reached a sort of a wall in trying to prove Boolean lower bounds, and even though there are continuous attempts, we didn't progress very much in the last 50 years. And the arithmetic world offers a more structured arena to prove lower bounds, because in the arithmetic model is more restricted. There are more identities. There are less identities there, and than the Boolean setting. And there's all this machinery of algebra and geometry and so on, which we can use within mathematics. So hopefully it should be easier. And so that's why we are studying this. Of course, the other great reasons are that everybody needs to solve this kind of problems, linear algebra, various evaluations of polynomials in coding theory, and there are lots and lots of good motivations to study arithmetic computation. So what is arithmetic computation? I'm going to work only with the non-uniform model, so these are just a circuit model. So, arithmetic circuits look something like this. Plus, I don't know, whatever. And then we have, in the leaves, the inputs are maybe, x7, x17. We can put constants from the field, -5. So it has to be an element of our field, and x1, and so on. So we are allowed to take the inputs. Very good. Yeah, I was hoping.
Just going back
In some cases, it's a direct reduction, and we will see later why you know, the non-commutative setting is more restricted than the commutative setting. It has less identities. It doesn't have xy equal yx.
Right, but
yeah. So some
idea of
you're right. You're right. But yeah. So I didn't say. You know, it's not a formal statement, but often having less identities is, yeah, makes it harder to compute things. Yeah.
What identities exist in the Boolean world that do not exist in the
X or x equals x. X or x.
Oh, x equals x.
Yeah.
Oh, I see.
Okay, so and that's a big thing. That's idempotency. Here, x squared is not x, and yeah.
What's your rule about division by 0?
Yeah, so we'll get to division. We'll get to division by 0. We don't allow this. Believe it or not. Yeah.
The gates are bounded, Fanny?
Yeah, the gates are bounded Fanny. So like Fanny 2 or 1. Okay, so that's how its arithmetic circuit looks like, and it computes some function. Quite a bit of the time we will not deal with division, and we'll soon see why. So we'll focus on the first three, and in which case this kind of object computes a polynomial. And it's very important that when we talk about arithmetic computation, to distinguish it from computation in the Boolean setting, another thing which makes it easier to prove lower bounds, is that what we are talking about is, so let me remove this division just for a second. So in this case, this will be a polynomial. So I wrote here a field f. Throughout, you can think that everything is happening with, you know, happens with coefficients in some field f. It wouldn't matter for most of the results. I'll state what is a field f. For some results, it does matter. So you're computing here a polynomial in the variables. And what I mean by compute, it means I don't care about evaluating this polynomial on particular inputs from the field. I really care about generating the formal polynomial that comes out here. So well, if I had x times y, and this y, but anyway, the point yeah, maybe example is not really needed. But the point I want to make is that in the, you know, the polynomial x to the p minus 1 is a polynomial x to the p minus 1, even if we are working modulo p. Okay, it's a formal polynomial. If we were evaluating this function in the field of p elements, it would be the 0 function. But I care about it as a polynomial. So we care about the monomials generated in this process.
What do you say is the justification for that?
Excuse me?
What do you say is the justification for not allowing identity x?
Yeah, so I mean, most of the time we will work with big fields, but yeah, the justification is that if we are ever going to prove that p is different than np, we are in particular going to be able to prove lower bounds for this model. So that's one justification. Another is that, you know, you just need to compute polynomials in this formal sense often, so might as well study it. Okay, so now I want to start to get into complexity thing, and there are two main complexity measures that we will look at. So this polynomial here is computed by a circuit, let's say with, I guess, six gates. Okay, so we'll denote by S of f the minimum size of a circuit for f. The size is the number of gates, let's say. It doesn't matter really if we have bounded Fanny. And there is another notion, which is L of f, which is the minimum size of a formula. And what is a formula? A formula is this kind of thing is not allowed. you're not allowed to have a gate with fan out 2, with fan out bigger than 1. So a formula is just a tree. If I wanted to compute the same function here, if I wanted to compute the same function here by a formula, I would have to do something like this. Well, maybe not have to do, because maybe there are cheaper ways. But if I just wanted to make this a tree, I would have to duplicate things. I would have to do this was x7, I don't know, x17. Here will be x17 again, and -5. But here I would have to just replicate this later bit. So I would have to write again plus and x17 and -5. And so on, right? So it will be a tree. So formulas are weaker objects than circuits. They are less concise. So this is always greater or equal to this. Formulas, of course, are more prevalent in mathematics. They, you see them more. But circuits for computer scientists are more natural. And anyway, the important thing is that they capture two very basic notions. I mean, if you think about the Boolean setting, but also in the arithmetic setting, circuit size captures time on a Turing machine. Okay, so that captures time. And formula size captures two things. It captures parallel time, how fast can you evaluate something in parallel, and also space complexity. So small formulas correspond to small space complexity. So this is space and also parallel time. So we want to understand both measures for, a bunch of natural polynomials. And we have complexity classes associated with them in the obvious way, and I will call them here P and NC, but I'll put it in quotes. And the reason I'll put it in quotes is that there'll be many models. I will start with so these have meaning in the Boolean world, and the analogous meanings that in the various models I'll use will define this in this. I mean, it's polynomial size, and also here it's polynomial formula. So polynomial circuit size. This polynomial formula size. Okay.
Where to say this formula size is capture of running time when space is limited, right?
Yeah. So yeah. If you have in the Boolean world, if you have formulas of polynomial size, then you could evaluate this function in logarithmic space. That's it.
Yeah, but it doesn't go the other way.
It goes the other way, and that's a good point. I'm going to cheat a little bit between polynomial and quasi-polynomial when it really doesn't make a difference. So yeah, up to this, because we are, as usual, we don't know exponential gap. So it will come up, yeah. Okay, so so I didn't say anything yet about division. I want to talk about these objects, and just I have to do some examples, and just to make sure that at least we have some okay, what is my favorite question? What's the most important polynomial in mathematics? All right, everybody agrees. So what's the determinant? So we need these definitions anyway. Determinant n of a matrix X, you should think of X as n squared variables. Determinant X is sum over all permutations okay. What's the complexity of this polynomial in these terms? What's the smallest size for a circuit computing the determinant? N cube, yeah, that's very good, N cube. Everybody knows this circuit? What's the circuit? Gaussian elimination. That's very simple. It's an N cube algorithm for computing determinant, but it's not exactly of the form I want because I don't allow you division, and Gaussian elimination has division. So is there a polynomial size circuit without division for determinant? What? Well, we are talking about the arithmetic world, so you're talking about Boolean. Yeah, no, that's true. It works, and so there is an algorithm. We'll actually understand better why this has to exist soon, but there is an algorithm without division. So many people don't know that. Yeah. Yeah, so if you think about what we are doing, where these are generic elements, let's say it's it's an n by matrix of variables, and the expressions you get are never zero, are never identically zero, so you can do this. So that's all we care about here. You are not, in this circuit, you are not allowed to divide by something which is identically zero, right, as a polynomial, or as a, whatever. Yeah. Okay, so what about formula for this? So
But if you perform Gaussian elimination on formal variables, would you get, and you use divisions, would you eventually get a polynomial or a rational function?
in the case that you are computing the determinant, you will get the determinant, which is a polynomial. That's what you are computing, so that's what you'll get. Sure, yeah, you can eventually clear the denominator somehow and get that. That's what this algorithm does. Yeah, indeed. But you don't need divisions. So this is just so I'm still plus minus times. The other question is, can determinant be computed fast in parallel? Is there a short formula? Let's say if we wrote the determinant as a formula, just expanded it, it would have n factorial terms. But is there but that would be depth too. I mean, can we have a formula of depth polylog that it's much smaller than exponential? We don't know. But less than exponential. Yeah. So again, that's something that people in arithmetic complexity know very well, and that's a very important result. So maybe it was first proved by Phil, and here Phil was the first to prove it, and then Berkowitz actually showed something stronger than this. He showed that there is a circuit of polynomial size and log squared depth. This alone implies log squared depth because you can always balance formulas, but actually you can achieve simultaneously polynomial size and log squared depth for determinant. So that's a non-trivial result. I mean, it's not difficult. Yeah. The determinant is not P complete. The determinant is sort of NC2 complete. Yeah, but this. Yeah, I will explain. Yeah, lots of things you know. In the Boolean world, we don't. No. Yeah. Oh, sorry. I'm sorry. Yeah, in the Boolean world, we don't know and don't expect, and that's what I want to get. But let me continue with the examples. Everything clear so far? You want to move over there, so I see you. The second most important polynomial in mathematics is this one, the permanent. It's the same thing, only without the signs. What's the best complexity we know for this? The best we know is something like n squared 2 to the n. So we don't know better than exponential size bound for this, and there's a good reason for this. The reason is Valiant's theorem that says that the permanent is NP complete. So I didn't say, here I had just the formula size and so NCNP, but there is also a class which can be defined that I'm not going to define actually, NP, and for the arithmetic world. And for this class, the permanent is complete. So permanent is NP complete. So one way to think about a good definition of this class NP is, problems reducible to the permanent, and I'll define reductions. I will not define NP, but I'll define reductions. So yeah, Joe. What? Yeah, so it depends what you are trying to do. Sharpie is a Boolean class, but here we are in the arithmetic world. So this is like what's called VNP, Valiant's NP. Yeah.
But actually, the VNP is really a class that is more similar to Sharpie than to NP in the Boolean world.
Yeah, that's true. Yeah, there's yeah. There is no analog of Sharpie in the arithmetic world.
Yeah, I'm saying that actually this VNP looks more like Sharpie.
Yeah, it does look more like Sharpie. That's true. That's true. Okay, so I want to just give one more example, or maybe I'll wait with it. So anyway, we have this. So now I want to start building the, sorry.
What is
And I forgot Andy, what?
what is the notion of efficient verification?
So I will say just, the reason, one way to, I'll give you one definition of NP for polynomials. We are talking just about polynomials. This, so first of all, let me make a point here. These two polynomials, notice that they have n variables and degree n. And in general, throughout everything I'm going to talk about, the number of, the degree should be polynomial in the number of variables. I don't want it to be bigger. Why not? I mean, you can encode the polynomial, describing the polynomial x to the 2 to the n. You can describe it by n bits, so maybe it should be allowed, but it shouldn't be allowed really because, let's say, this clearly requires exponential size formula. It's sort of a triviality. You have to do n multiplications, and it's, So we are just allowing polynomial degree, okay, like in this case. So you ask what's efficient verification for this. So think of a polynomial of n variables and, let's say, degree n, like determinant or permanent. And let's assume it has 0, 1 coefficients. That's the kind of class that, it's nice to have 0, 1 coefficients because it fits in every field. So it's, one way to define the class of polynomials here is to say that the coefficient of every monomial, if I gave you a monomial, there is a polynomial time algorithm that tells you whether it should be a 1 or a 0. Okay? So if you can define it, of course this can be done here very easily. You just, or well, maybe there are minus 1. Anyway, you could tell, given a monomial, what's its coefficient. The class of all these polynomials are the VNP. Okay.
So it's polynomial in the size of the...
Polynomial in n. So n is the number of variables and also the degree. And the circuits, which are Boolean circuits, they just tell you, given a monomial, what is the coefficient for Boolean circuits. Yeah.
I'm familiar with these easiness and hardness results you stated in the commutative world. How much of what you just said is also works for non-commutative analogs of P and
Yeah, so I'm going to say all these things. So now I'm going to... Yeah, I'm here as a commutative, but these will be my examples also in the non-commutative. And will, yeah.
Do we know something about L permanent of n? Smallest L?
We know the same bound. I mean, this riser, well, riser is not really a formula. It's probably... yeah, actually, it's true. There's a it's a depth-free circuit, but it's not a formula. Yeah. What are you asking? maybe you lose, you don't lose much, so right, so you just, it will remain about 2 to the of n as opposed to n factorial. Yeah. So I want to start, so to build structure to this, not sure if okay, let me start here and see if one will be enough or not. So, yeah. No, there are no counting arguments. I mean, no, there are counting. Random polynomials are hard. Yeah, they are dimension arguments. They are not quite counting arguments. They are dimension arguments. It's very easy to see that a random multilinear polynomials on n variables requires exponential size. Yeah, yeah. It's slightly more tricky than the Boolean world, but you can do it. Yeah. So I want to give some structure to, to this complexity and complexity classes. I want to talk about what's known, and I'll start with the commutative world, and I'll start with here with just plus times, plus and times, just without division. Minus is just like plus, right? Because we allow constants like -1. So I'll talk about the best circuit lower bounds, best formula lower bounds. This will be one type of results I want to talk about. Then I want to talk about completeness results or hardness results. So I want here NC hard and P hard and P hard. Then I want to talk about, so we'll soon do it for for all these cases. I want to talk about this P versus NC question. Can everything that has sequential computation can be efficient sequential computation be efficiently parallelized in the arithmetic setting? That's one basic question we care about. The other basic question, of course, is P versus NP. And I also want to talk about polynomial identity testing. So polynomial identity testing, or what's more general, a general way to call it is the word problem. We'll get to this in a second. And I also want to talk about division elimination. The elimination of divisions, and I'll explain what this is. But I first want to talk about these basic things for the case of commutative, the commutative world. So I'll state some results, and then I'll summarize them there. So what do we know about lower bounds for the general commutative case? One theorem of Strassen and Bauer and Strassen is that, so I'm going to do very few proofs today. I'll do more next week. Some of the things I'll talk about today, I'll prove next week. I just want to somehow fill this table of what we know in the commutative world and the non-commutative world. Various functions have lower bounds of degree, which look like n log n. So what, for example, the determinant, if you want n variables, and determinant is root n by root n. So the size of this, and other, for example, x1 to the n. And there are other examples. So there are explicit simple polynomials which have a superlinear lower bound. This is something we don't have in the Boolean world. So there's something we can do which is a little better. So here we have some n log n lower bounds, explicit n log n lower bounds. But we don't know anything better, and these results are 40 years old. So it's time somebody did something about it. For formulas, as old the result, I forget the name, Kolkoti. Yeah, Kolkoti. But this is really the same as Nechipuruk. Maybe I should write. Yeah, I should. just for the record here. So these names. So this is Strassen and Baustrassen. And this is Kolkoti. But it's a method of Nechipurk. Showing a formula lower bounds which are slightly better. These are quadratic lower bounds. I think that here you can put the element distinctness function, so pi I less than j, xi minus xj, quadratic. So it's a little better, but that's all we know. So again, and these are very, very old results. So anyway, we are stuck there. So let me add this here. We have n squared lower bound. So the first challenge for you is just to improve these. Now,
Did you just put the determinant again?
I don't quite know it. Probably true, but I'm just trying to write things that I'm sure of.
Will just be a reduction?
But it may cost, since we are not, it's not about polynomial bounds, it's about, you know, I mean, the reduction may be costly. We'll see in a little bit.
It would be for an n by n matrix, and then it's n squared.
Yeah, so it's not, yeah, you have to be, yeah.
I less than j less than square root of n, or less than n?
N variables. Yeah, it's the same, this is the same function for which in the Boolean world, if these are log n bit integers, you also get quadratic formula size by this Nechipurk argument. It's just a sub-function counting, very simple. Okay, so we know some lower bounds, but as I said, are weak. And then the next set of results about completeness come from Valiant, as I already mentioned. So in the late 70s, Valiant introduces arithmetic classes, and he showed that permanent is NP hard, and determinant is NC hard. So I want to state this more precisely, and in order to, and in fact they are, you know, this is complete really, it's not just hard, and this is almost complete if we don't care about polynomials and quasi-polynomials. But I want to start saying more formally what it means to be complete or to be hard, and for this we need a notion of reduction, right? A notion of reduction, just like in the usual Boolean complexity, we have you know, polynomial time reductions, Karp reductions, Cook reductions. Here we have Valiant reductions. Yeah.
You said that for palindrome or by counting arguments, you also get lower bound?
Exponential lower bounds, yeah. Yeah. So that, you know, it's the same story in Boolean complexity. Random functions are hard, and we know it. But we are trying to figure out explicit, you know, for any. Yeah, that's the best we know for explicit functions. Okay, so good. So what does it mean? So we need the notion of reductions between polynomials, and Schumann Valiant it actually started with Valiant, but there is a paper, a really beautiful paper, sort of completeness classes based on linear algebra by these guys. And you want a reduction, and the reduction, since we are anyway in the non-uniform case, we are going to allow non-uniform reductions. And these reductions are going to be the simplest you can think of it, just by linear projection. So you have two polynomials, f of x1 up to xn, let's say, and g of y1, ym. And you want to say, what does it mean that, so which should read f is easier than g, right? And easier is really not much harder. Just like in the in Boolean complexity, the fact that we have polynomial time reduction means we add a polynomial amount. It may be a bit harder, but not much harder. So what is this reduction? Simply, if you can get G to compute F for you, and you can get it cheaply, and the cheapest way is simply have linear transformation translating the x to the y variables. So more formally, there has to exist A1, A2, AM linear functions. And you can sometimes, the right thing is to take affine functions, but we won't need this distinction. You need this such that f, when you want to compute it on an arbitrary input x, one way to compute it is simply to compute G on A1x, A2x. So this is the inner product, right? A2x, AM, AM. Vectors, yeah, it's all vectors. So here, x is x1 through xn. Yeah. So you just have a linear. So what happens is that G computes f for you on some subspace. The appropriate subspace tells you exactly what f is. So that's a linear projection, and this is fantastic. That under such a natural reduction, so it's clear what the reduction is, right? So under such natural reduction, simple reduction, these guys are complete for these classes. I want to stress that this is really a good reduction in the sense that if we had a simple circuit for C, in order to compute f, we just have to compute these affine functions, which is another, I don't know, m times n computation. So it's certainly a good reduction. And under this natural reduction, we have this complete problem. So if we write here, so I started writing, we have a complete problem here, and we have a complete problem here, which means that to us the P versus, if you want, we will soon see that it doesn't matter, but you can ask this also, NC versus NP. If you want to ask this question translates to just a very simple question about the existence of a reduction between permanent and determinant. So there is equality here if permanent n is projected, is reducible to determinant poly n, n to the order 1. So we have this very clean question, like we have, if clique was reducible to max flow, then P would equal NP in the Boolean world. So here we have, if there was this type of really simple reduction between permanent n and a determinant, which is polynomially bigger, then P will be P actually will equal NP in the arithmetic world. Yeah. That's a very good question. And the completeness, the fact that this is complete means yes. Yeah. So permanent. Yeah. So let me. So I should. Yeah. Very explicit. And I will show you this result, but I will state this result. So what? Okay. So what did Valiant show? So this is 1 and 2. So 1 says that if some polynomial is, well, let me call it VNP because that's the name of it. So this is the class Valiant defined that I just explained. Let's say 0, 1 coefficient polynomials, where these coefficients can be determined easily by some algorithm. So P is reducible. So Pn, let's say, on n variables, permanent n to the 10. And this is explicit, completely explicit. So in particular, determinant can be done because determinant is also a polynomial here. Yeah, so it's one of the most non-trivial reductions that we know. I mean, there There are zillions of reductions in complexity theory. That's one of the most non-trivial ones. Beautiful reduction. It's not that complicated. We understand it much better today, but anyway.
So, Avi, should we think of the A1 all the way up to AN as matrices?
So these are vectors. You can think of this as a big matrix transforming. So you can think if you put A1 here as a row, A2, AM. If you think of this as a matrix and you apply it on x1, x2, xn, you get the vector y1 to ym that you should insert to G in order to know what f is.
So the inputs for F and G are not vectors?
No, the inputs are not vectors. x1, xn are variables. I just encoded this set of variables by a vector. Yeah. Okay, so that's what you know. So all you need to do pre-processing in order to use G to compute f is just do this linear transformation. More questions? Good. I like the.
Do you actually need general linear confirmation?
Do I actually need?
Isn't it enough to just have copies of variables of like 0 and 1?
Yeah, it's easy enough. We'll soon see. Yeah. So, yeah.
This kind of a reduction seems very restrictive. I mean, okay, so if you have a good algorithm for one, you have the other.
Yeah.
Maybe even if you don't have this kind of a reduction,
Mm-hmm.
if you have something efficient for one.
Yeah. So it's
So
all.
why do we consider
This is great. So you asked two complementary questions. He wanted to simplify the reduction, and you want to generalize it. And the great thing is that it doesn't matter. And that's the beauty of it. So the reason I like this definition is that, you know, it's the most natural to mathematicians. Linear projection is the most natural to mathematicians. As it turns out, one can allow not just, you know, every entry here is a linear form. One can allow, instead of linear form, just taking one of the variables or a constant. I'll show you an example in a second. So not general linear forms, but linear forms where these A's have only one non-zero in them. On the other hand, so you can restrict it and you don't lose generality. On the one hand, on the other hand, you can generalize it. You say, why don't allow, I don't know, quadratic polynomials? It's also not very costly, or cubic polynomials. And as it turns out, and that's because of the completeness of determinant, if you allow your whatever thing that has small formula size, arbitrary polynomials which don't have large formula size, then it's not a more general definition than this.
Okay, but this is only one generalization when you plug
Yeah, you can look at other generalizations.
I mean, reductions we have in different models seems to be stronger.
No.
You can
No.
have
No.
any polynomial mapping that's efficient as a small circuit. And you get
Not, yeah. So it's not more general. It's not more general. We don't gain generality by making it. Yeah, so that's the beauty of this. Okay, so because we have this, so I stated so there are two statements here. We already saw, but to what Ori was asking, that determinant n is reducible to permanent and to the 10. And we have the question there of whether permanent is reducible the other way. And that's a big P versus NP question in this domain. But we do know, so, I mean, that's a concrete problem. So we can try to prove lower bounds. And at least maybe try to prove lower bounds for small n. And I mentioned this in the talk last week. I want you to notice, so we have this question of permanent and determinant. We don't know this, but you know, for small n, it does work. If you want the permanent of A, B, C, D, you can compute it by computing the determinant of A minus B, C, D. Right? So, and this is clearly a linear projection. Yeah.
Right, I'm one of Valiant, though. You mean that P reduces to permanent size, and the 10 where n is like
Yeah, it is a complexity, but I'm sort of assuming, yeah. So, okay, so you're right. So let me write it more better. If P is such that S of P is S, then permanent S to the top. Thanks. That's a better, more. No, no, I mean, it was just false. There's no difference. The previous statement was not. Yeah, you want to relate here the permanent to the size of the smallest circuit, identifying the coefficients of P. Okay, so this is, I mean, the complexity of the coefficients. Right, but I want to say that this question, so this kind of reduction may suggest that you can continue maybe by induction, but anyway, it's false. You cannot reduce permanent of 3 by 3 matrices to determinant of 3 by 3 matrices. That's easy. And then people started proving lower bounds on the size of the smallest permanent, size of smallest determinant that can encode permanent in this way. And we have some lower bound. And there's a really great theorem of Mignon and Rassaer, two French algebraic geometers from a few years ago, showing that permanent n does not reduce to determinant less than something like n squared over 2. You need at least a quadratic blow-up in the size of the matrices. Okay. It's a great result, but I should tell you that this is, despite that, despite the fact that it looks like a quadratic lower bound, it's actually a linear lower bound because there are n squared entries here. There are n squared variables. And it turns out you can prove the same lower bound for the second symmetric polynomial. You can prove it. But anyway, it's nice, and the technique is nice. Yeah, it's a beautiful result. Going beyond this, maybe many of you know, is one of the approaches that is well, it's hard to say where it stands, but at least it became a sub area and very active. Is the GCT program. So here we have the GCT program of Malmali and Sohoni, which is trying to establish such lower bounds about such reductions using algebraic geometry and invariant theory. And one curious fact is that even though this is a commutative world, and it's generating questions in commutative algebraic geometry, somehow, when we are done with all the non-commutative stuff, I'll show you, you'll see that you get to actually, for completely different reasons, to the same questions or to similar questions they are asking themselves. So it's really interesting. Okay. So let me, so we talked about this question. I want to talk about this question. So what's this NC versus P question? It's, again, the question of whether everything that can be computed efficiently in a sequential manner can be computed efficiently in parallel, right? Can be parallelized efficiently. And here comes the result of Valiant, Sciom, Berkowitz, and Rakov, early 80s. Somehow, against all our intuition in the Boolean world, here you can efficiently parallelize everything that's efficiently computable in a sequential way. So you take a circuit, you can make out of it a formula. What we saw happen for the determinant here is not a coincidence. The mere fact that the determinant has a polynomial size circuit already says it has a polynomial size circuit of low depth. So that's a general reduction here, that the statement is that if S of f. So remember, f is n variables, polynomial n degree. S of f says that f has a circuit of size, well, roughly S. So S, let's call it Sn, and polynomial in Sn, and simultaneously depth log n squared, or really log n log s. So in particular, what? No, it's log s, and here it's log d. Yeah, but d is polynomial in n. So right. So in particular, this means that L of f is at, I should have said polynomial in n. Let me just simplify. Then this will be polynomial in n, and this will be log n squared. And it means that this is at most n to the log n, and to the O log n. Okay, so it immediately has short formulas. So this is a great result, and I want to say something about this result, because many of the results, I'm not going to give many proofs, as I said, but I want to explain what happens, why this happens, first of all, and why it will cease to happen later, and how many of the results that I will not show you work. It turns out that we have a much better understanding of arithmetic circuits than Boolean circuits because of the notion of degree. Okay, we can, there's another notion out there that doesn't exist in the Boolean world that we can access. And because of that, we can take arbitrary circuits that in the Boolean world look like a mess and we don't understand them. And we can, in the arithmetic case, we can simplify them because of this notion of degree. So I want to tell you one result that actually leads to this. And this result was more or less, I guess, implicit already in Yehudayoff's work. I mean, he didn't have the size efficiency, but it was in Yehudayoff's work. So it's a theorem. And you can try to prove it. It's not very difficult, but you can see why, the arithmetic structure gives you this kind of help, or where the S algebraic structure helps. So assume that you have a polynomial whose size is at most S, and let's say the degree of f is d. Okay. Then f can be computed in a very simple way. F can be written as a sum. I goes from 1 to s, so just the same number of terms as the number of gates in the circuit. Gi, hi, so product of polynomials, such that for every I, degree of gi and degree of hi are between n over 3, d over 3 and 2d over 3. So you can somehow split things in the middle according to the degree. It's not really difficult, and also you can see that if you have this result follows immediately. You just continue. You break up the. Right? Okay. Anyway, so that's the kind of thing we can do. We can do it even better for non-commutative circuits, as we'll talk about later. We get more structure, and hopefully this structure is used to prove lower bounds. I should say, for example, that there are analogous results, or stronger results, if the circuit, if the function has a small formula. Then you can also have some decompositions that I'm not going to tell you. This decomposition exists in restricted models like the multilinear model. And it is essentially the reason that Ran can prove super polynomial lower bounds for multilinear formulas. It's because they are simple enough that they admit such a decomposition into sum of few things which look simple. And then you can sometimes prove lower bounds. One would hope that this alone should be enough to prove lower bounds, right? Yeah, I mean, when you first see it, it looks like it's highly restrictive. But anyway, we don't know better lower bounds. So I just want to finish this column and tell you, and we take a break. Yeah?
Is it known the two questions are completely independent, P versus NC, P versus NP?
As far as I know. Yeah, I don't know a connection. So here we know that P equals NC, as I said. It's a very peculiar thing. I want to just say two things about this. So these are actually, it's good that it's on a different board because these questions are of a different nature. These are all arithmetic complexity questions. This one is a Boolean complexity question. What's a Boolean complexity? I give you a description of a circuit for, of an arithmetic circuit, and I ask, does it compute the identically zero polynomial? Okay, so this problem, PIT, polynomial identity test, polynomial identity testing, is the question of given when a circuit C the question is, does C compute the identically zero polynomial? So it's polynomials. I want to mention that I wrote the word problem. This is a particular algebraic structure, polynomials, right? We are in the algebra of, I erased it. Anyway, we are given algebraic objects and we ask whether it's identically zero. This is more or less the same as asking, is C1 identically equal to C2? It's a slightly more general problem. I give you two circuits, so they compute the same polynomial. This is a basic problem in every algebraic structure, and it's called the word problem. If I give you a word in the generators of a group, does it compute the identity element? Right? That's a word problem for groups, the word problem for rings, the word problem for all these structures. So this is just a special case. And I give you some description, of course, of the object, not necessarily the obvious description. So that's a basic problem. And we know that this is it's a basic result of the Milo-Lipton and more familiar and as Schwarz-Zippel, and was also recognized by mathematicians before these things, is that PIT is in BPP. There is a fast probabilistic polynomial time algorithm that can tell you whether an arithmetic circuit computes a zero polynomial. What do? You just apply random numbers there. I mean, if it's not identically zero, then it's some variety of measure zero, at least in over large fields. And anyway, I'm not going to explain it. It's a simple result, and you don't even need to think about picking real numbers at random. Small integers are fine. Everything is fine. So that's a basic result that I'm sure many of you know. So I just want to write it down because this is in BPP. This works even in the black box model. You don't really need the circuit. It's just an evaluation. Okay, and the last one I want to, yeah. Exactly, yeah, very, very good, very good. Well, here it's not undecidable. Here you can expand the circuit. If I give you the circuit, you can expand it and see whether all the coefficients are zero, because we said the degree is bounded, so you can I mean, certainly exponential time you can do it, right? But it turns out that here you can do it much, much better in the BPP. Yeah. But it is, in some cases, it's undecidable, absolutely. This word problem is a fundamental problem, and its decision, you know, whether it's decidable even is sometimes non-trivial, and we'll get to this. The last thing I want to say, well, let me do it after the break. Okay. Okay. So let me continue with the last item on this column, and this is division elimination. What do I mean by that? Why do, you know, since, I don't know, 1975 or something like this, everybody doing arithmetic complexity in the usual domain, in the commutative domain, ignores division completely. And the reason is a great theorem of Strassen that says that, you know, if you are computing polynomials like determinant, you shouldn't worry about division. I mean, if you have an algorithm with division, you have another one without it. Okay, so the theorem of Strassen. So if f is computable by a size S circuit with divisions, so f is a polynomial. With division, then it is also computable by a circuit roughly of size S d squared, so d is the degree of f, without division. And I may show you this next week when I talk about eliminating divisions in the non-commutative case. It's a beautiful and simple idea. Yeah.
Why is it desirable to eliminate division?
Well, it's the most, I find it extremely natural. I mean, you're computing a polynomial where there is no division, so why should you ever need division? You would like to, yeah. So the other thing is you don't want to accidentally divide by 0. When you're actually evaluating something like Gaussian elimination, you have to, you know, who else is only, you know, you have conditionals, you know, if it's not 0, then you, yeah. I mean, what's amazing is that it's true. It's not, I find it quite amazing. That's true. It's a simple proof, but it's beautiful. And, well, you can think about it. Suppose you don't know the proof. How would you do it?
Personally, I find division hard.
Right. So check. We can eliminate divisions efficiently. OK, so I want to move to the so here we denote the algebra f of x, and now I want to go to the non-commutative computation, still with only plus and times. And here the algebra is denoted with, you know, this kind of brackets for some reason. I mean, definitely to distinguish this. So let me just talk a little bit about this non-commutative world, because there's something now we have to make more precise in the definition of the model, in the definition of the object we compute, and so on. So what's the most important thing is that in our variables, you know, x1, x2 does not, we cannot already assume that, you know, generally xy. We cannot assume that they are equal. We cannot use it for cancellation. And this already shows immediately that this model is weaker. A non-commutative model is weaker than commutative case, at least by a simple example. Suppose you are trying to compute x squared minus y squared, and you want to just count how many multiplications you need to do this. So in the commutative case, we can write it as x minus y, x plus y, right? So it requires just one multiplication. Whereas in non-commutative, you can convince yourself that's a lower bound. You can prove it needs two, right? You need to square this separately and square this separately. So it's a weaker model. Okay, we'll see a better demonstration of this fact. So that's one thing that we need to know. The other thing, going back to this, it tells us that monomials now should be ordered, right? So when we are describing a polynomial, we should say what is the order of multiplication in the polynomial. So for example, talk about a determinant. This definition of determinant, if we really multiply it in the order from 1 to n, then it's called the row determinant. We first multiply the element from the first row by the element of the second row, and so on. And this particular version of determinant is called the Cayley determinant. But you could choose another. You could do by column. You could do, there are lots and lots of definitions of potential ways of expressing what is the determinant in a non-commutative set. That's a very good question, and I'll answer it in a few minutes. Yeah. So, but anyway, you have to define it. And similarly, when you have a circuit, and in your circuit you have a multiplication gate, you have to say who's coming from the left and who's coming from the right, obviously. Okay, good. So, but with this modification to circuits, with this understanding of polynomials now, where the monomials, the order matters, we can start doing the same complexity theory. And we can ask ourselves, what can we say about all these issues? And we can say more. What?
Did you define the non-commutative, determinant, and permanent?
I said that I didn't define it because I said that there are lots of ways to choose them. In this order, they are called the Cayley determinant.
So when you have one monomial for each set?
You have the same monomials, and they are ordered by row. That's one definition. There are lots of determinants. There are quantum determinants and Capelli determinants, and people define them with various orders for different purposes, and they are all interesting in some sense. But I want to argue a little later that they are not interesting, and there's something else that has to be there. Okay, so.
You always keep the fact that addition is
Yeah, addition is commutative. I should have said this. Addition is always commutative. Because addition is really, yeah. Yeah, and multiplication remains associative. Those of you who really care, we also have a paper about non-associative, and there are results about, there is structure there as well. But in the non-associative case, I mean, there are reasons to look at it, but there are completeness results, but there it's easy to prove lower bound. So it's so easy, it's so weak that it's, so we remain associative. So we are working over these non-commutative variables. And that's the name of the algebra. So it's a linear span of these ordered monomials. Again, there are lots of reasons. I mean, besides the fact that it's an easier model and maybe we can prove lower bounds, there are lots of reasons to study non-commutative settings. There's non-commutative, well, in quantum mechanics, non-commutativity plays a big role. Non-commutative probability, there's non-commutative geometry, and there are lots of algebraic structures in which things don't commute, for example, matrices, right? So we really want to understand, let's say, polynomials in matrices, and this will come in. Okay, so what do we know? So we suppose we want some explicit polynomial, maybe the permanent determinant for which we will have a lower bound. I should mention, Rand told me that maybe one lower bound I put before, an n log n lower bound on the determinant of a root n by root n matrix, may not be correct. But there are other n log n lower bounds. So, like, what?
It's not known. I mean, it might be.
Yeah, yeah. Not known, I meant. I didn't. I wrote it as a theorem. Anyway, we have n log n lower bounds here. And of course, we have also n log n lower bounds here because it's a weaker model. But we don't have better bounds. And this is a great question, and I want to talk about, next week I want to give you examples of concrete problems that you can solve and that look much, much easier than circuit lower bounds and will imply exponential results here. But I won't do that now. What I want to say, and that's really important, is a theorem that I'll state of Noam Nissan. Formula lower bounds we can prove in the non-commutative world. Okay, so it's also extremely old. It's I don't know, 85 or something like this. That says that, for example, if you're trying to compute the determinant or the permanent or even the palindrome function, which I'll define. So this is non-commutative. There are non-commutative lower bounds on formulas. Yeah.
So when we make our model weaker, we often run into the chance that we render out our functions non-explicitly. Usually you want to prove lower bounds.
Yeah, but I mean, these are, you know, when I define it like this, clearly explicit, right? I mean, suppose you say that
be computed by circuits of,
the circuits are Boolean. The coefficients here are computed by Boolean circuits in the same way.
No, I mean, okay, you would want to say, if you want to say that lower bounds for determinants are maybe, or formula lower bounds for determinants are like P versus NC, we would like to say that the determinant, that this determinant can be computed by polynomial size non-commutative circuits.
No, you want to, well, the definition, if you are talking about NP, for example, Valiant NP for the non-commutative setting would be the same definition. What you are supposed, it's an explicit polynomial if when I give you a monomial, now it's an ordered monomial, so x1, x2 is different, but I give you the monomial, you tell me whether its coefficient is 0 or 1 by a polynomial size circuit.
Okay, but what about VP?
What?
Okay.
What about VP? So you have to, yeah, so.
Yes. Suppose I want to use the determinant to separate P from NC.
Yeah, so we will see an example like this. So you would like something, exactly, you would like something that's computable in P and not computable in NC.
Yeah.
Exactly, there's nothing changing.
Okay.
The questions are of the same nature, that's what I'm.
Yeah, what is the upper bound for determinant with circuits, non-commutative circuits? Or do we know an upper bound?
Yeah, 2 to the n. Yeah, so, I mean, it's probably a little worse, but yeah, anyway, yeah, maybe you meant whether it's n factorial or better. Yeah, maybe it's, offhand, I don't know better than n factorial. Yeah, ABP is something else, and I just want to mention. Right. Right, you're right. Yeah, that's right. So there is a 2 to the n, 2 to the O, and yeah, that's right.
So actually my question is, do we know an interesting function that is computable in non-commutative P, but we know any interesting lower bound?
Yeah, I'll show you such a circuit when I have division. Without division, I don't have offhand. Yeah, so I'll show you when I just want to mention, so that's a very, so, you know, this is great. That's a seminal paper. It introduces techniques to proving lower bounds for non-commutative circuits, not circuits, formulas. Circuits we cannot do yet. And the techniques, you know, it's the rank argument. And I just want to say something about it just so that you see why it's so much simpler than the commutative setting. Basically, okay, so let me define this palindrome function, and I'll explain what the rank lower bound is in this setting. The palindrome, what you have is you have variables x1, 0, x1, 1, x2, 0, x2, 1, xn 0, xn 1, and maybe the same with y's. It doesn't really matter. You have the same with y's, and what you would like is to represent, a string alpha and alpha reverse, more or less. So, or even alpha alpha, it doesn't really matter. So the monomials that you have here is the product, so this palindrome of these variables is the product I goes from 1 to n. So it's a sum over all, binary strings, alpha in 0, 1 to the n, of pi xi alpha I. So you have this, and then you multiply in this order pi from n, n to 1, yi alpha I. So you just have this, you're matching all these vectors, right? Why am I talking about this function and not just these functions? Is that unlike these functions, for which we don't have polynomial size circuits, this one we do. So it's very easy to see that the size of this non-commutative size of palindrome n is basically linear. So not only is it proving exponential lower bounds, it's also separating NC from P. Okay, so here we have. So unlike the commutative setting, here we don't. We cannot parallelize every efficiently sequential function. Okay? Let me not say anything now about the proof, because I want to at least today fill all this table up. But anyway, there's a very simple argument that can be thought of as a rank argument, and in other language as a partial derivative argument. But anyway, it's linear algebra showing lower bounds for formulas. Okay, so we know this. What about when we are in the non-commutative worlds? Are there complete problems? So a few years ago, with Pavel and Amir, we wrote a paper which sort of mimicked what Valiant did, and proved that now we are in the non-commutative world. Again, I'll just remind you, we are in this world. Still, determinant is NC hard or NC complete in the same sense. NC hard, sorry, it's NC hard, and the permanent is NP hard. So just it's the analog of Valiant's results. And maybe I'll show you this because it works just the same in the. Or maybe I'll delay it for next week. But anyway, it's just the same as in Valiant. The result here is pretty similar. The result here is more complicated, but nevertheless, you can carry on Valiant's reductions, and the fact that the monomials are ordered, you can cope with it. And this same Cayley, so the Cayley, I should say that this is, you should ask what, yeah, for example, the Cayley determinant and the Cayley permanent. Then we thought that, in some sense, this rubric was also filled. Cayley det and Cayley permanent. And there was a completely orthogonal direction that is very fascinating, and I can, maybe I should say some more things about it next week, of going back to just the normal permanent of, let's say, of integer matrices, which is a basic question. We know it's sharply hard. How about approximating it? So the question of approximating the permanent in the Boolean world. There's a beautiful paper of Chen and Sinclair, which took a bunch of previous papers offering some probabilistic approach into developing an algorithm that would actually do, approximate the permanent, have a polynomial time approximation scheme for the permanent. I should remind you that we know such a scheme. This is a famous result of Jerome Sinclair and Vigoda, but nevertheless would offer a completely different, algorithm for the same problem, approximating the permanent. And there was only one caveat in their approach. In their approach, they needed to compute the Cayley determinant with entries that are matrices. So n by n determinant whose entries are n by n matrices. And they couldn't do it. And the question was whether it's easy or hard. And the amazing thing that came a little later, so for us in our mind, this was sort of, okay, they are hardness results, but they are sort of completeness results. Arvind and Srinivasan, just a few years ago, maybe 4 years ago, proved that the Cayley determinant, so what we are used to thinking as the easy one, is NP hard. It's as hard as, in fact, what they proved is that permanent in this world. Now we are in the non-commutative world. So here the Cayley permanent n is reducible to the Cayley determinant. I don't know, n squared or n cubed, something like this.
Just for matrices or for any non-commutative?
No, non-commutative. You can write non-commutative.
What's the reduction that you're allowing in the non-commutative world?
Well, the reduction uses matrices. But if you could compute this arithmetically for non-commutative, you could also compute it for matrices, and that would give you an answer here. So it's, what I'm saying is something weaker than they proved.
What do you mean by linear projection for the non-commutative? It's just the same?
The entries in these matrices are linear functions of the... Okay, it's a good question. So there is a statement that makes, it's a good, I should check exactly what it means, but somehow in the non-commutative world, determinant, at least the Cayley determinant, is as hard as, permanent. So this is really weird. So first of all, we should write it down. Cayley determinant. And once you realize this is not very useful, the fact that it's hard here. And in fact, you can say something about this type of matrices that arise here. They are nearly triangular, so they look like this. They are nearly triangular. They are triangular, and there is just one diagonal containing ones just below the diagonal. So this, at least the hardness here, or the maybe completeness here, is for simpler objects.
Do we know any complete problem for NC?
No. Okay, so here, it's not clear what, because both of these are hard. We don't have good complete problem. I mean, a good question is whether this is reducible to this, to the triangular case. I'm not sure. It's so interesting, I won't write it down. But anyway, we have this weird phenomena there. And now I want to talk just a bit about these two things, where here I'm not allowing division, so so this is meaningless, but I want to talk about PIT. So it really matters. So I said before that the probabilistic algorithm for checking whether a polynomial is identically zero works in the black box model. If it works, if you are given a description of the circuit, then the question is, what are you giving? A circuit, a formula, an arithmetic branching program, and then it matters. So let me not talk about this. So Let me restrict myself here to the black box case. Black box identity testing. So you want to test whether a polynomial is identically 0 in the non-commutative world. And here comes something really bizarre. You already seen it, so it shouldn't surprise you, but it's not completely clear that it's an easier problem in the non-commutative setting because 0 occurs, x1, x2 minus x2, x1 is not 0 anymore. It is a legitimate polynomial, so you shouldn't, so anyway, it's not clear. And what's worse, or what's better and makes life really interesting in the non-commutative world is that there are polynomial identities. So I have to say, so what I mean. So you take such a non-commutative expression like x1, x2 minus x2, x1, and it will be 0. It will equal 0 if we are working over f, right? If we evaluate it over f. So let me write it over m1 of f. If we have 1-by-1 matrices over f. But if we can evaluate any such, that's one of the purposes of studying non-commutative polynomials is what happens when we evaluate them on the most natural non-commuting objects we have, which are matrices. When we evaluate this in 2-by-2 matrices, then it's not identically 0. So it turns out, and that's a theory developed by Mitzur and Levitsky, that so you can start asking yourself, so are polynomials, 0 over, matrices of a certain size, like happens here, and does it continue? Does it go high? And it does. And here's one polynomial that is called the standard polynomial on n variables. It's like the determinant. It's sum over all permutations. But now there is no matrix. There are just n variables. And what you're doing is multiplying in order the elements according to the permutation pi, in all possibilities and with signs according to the sign. So you have all monomials, all possible n factorial monomials, and you just evaluate them. So this is Sn. This is a polynomial. You should notice that this is S2, right? And it turns out that S2n vanishes, is 0 on all of Mn of f. So it's, so we have these objects. They are non-zero, but they are 0 on every polynomial. But what Mitzur and Levitsky also proved, I think this was known, but this is 1950.
So what's the difference between this and the Kelly determinant?
Well, it's not an n by n matrix. It's just n variables.
Oh, I see.
It's just, there's no matrix, no ij. It's only one index here.
Oh, I see.
Yeah. So this is an exercise. You can check this. And the Mitzur-Levitsky theorem says that no. So this is a polynomial of degree 2n that vanishes on all. If degree of f is less than 2n, then f does not vanish. On whatever, Mn of f. Okay, so it's tight. This result is tight. Maybe I'll show you the proof. There are several proofs that are really nice. But this tells us what to do.
So you're using n for the size of the matrices as well as the number of variables. So is there a relationship like?
Yes, so I defined Sn. Now I'm using S2n. right? So S2n is a polynomial of degree 2n which vanishes on all matrices. It's just matrices. The matrices over the field. Oh, no, n.
So if I make it 3n, will it continue to?
No, so that's why I'm saying it's not. This is a tight result because if you evaluate any polynomial, not just the standard polynomial, but any polynomial whose degree is less than 2n, it will not vanish on n by n matrices. So it's important, yeah, this n is important.
No, I'm still confused. So the number of variables is n, like the number of formal variables.
In Sn, the number of variables is, it doesn't matter. Yeah, this does not matter how many variables there are in F. Yeah, just the degree. Thanks. Yeah, that clarifies it.
So just by looking at one non-vanishing coordinate of a matrix, you can already say that you have a short swivel type BPP test.
Yeah, very good. So that's exactly what we want. So this completely tells you what to do if you want a BPP algorithm for now polynomial identity testing in the non-commutative domain. If your polynomial has degree D, take a random matrix of dimension slightly bigger than D over 2, let's say of degree of dimension D, and yeah, this will work the same way because it will be reduced to the commutative case. So this in BPP. Because that's eventually you reduce the question to a commutative situation where the commuting elements are the entries of the matrix. The fact that it never vanishes really means that the fact that it doesn't vanish means that on a random matrix it doesn't vanish.
Well, you could say that if you substitute in matrices and let them be matrices of indeterminates, then the resulting product, the
Exactly.
value is a matrix of
Exactly,
polynomials.
commutative, exactly. And since you know it's not identically 0, you know that the random one is good. Exactly. So it gives you a reduction, and it's a cheap reduction because this n is just a degree of. All right. Good. So finally we are into the, I just want to fill this table here. So now we are into non-commutative with division. Plus times and divide. So this is, I'll continue next time, but I mean, this brings us into the most, I would say, exotic world of non-commutative rational functions. And I'll just tell you some things about this world, and just tell you what we know, and then we'll discuss it more next time. But it's really bizarre. So it has a name, this, or has a symbol. And you should think of this symbol as sort of generalizing the fact that when we take the usual algebra and we look where we make a field out of it, a field of fractions, so we extend polynomials to rational functions in the usual way. This is denoted with curly brackets, so that's what happens there. But let's stay here. I just want to remind you that in this world, in the commutative world, the situation is really simple. Every element here, every element is of this form. It's a ratio of two polynomials. There's a canonical and minimal way to write an element here. So it's really simple given polynomials. It's just a ratio of two polynomials. This stops being the case here. So I want to sort of give you a few examples to convince yourself of this. So let's look at, so what we are allowed to do is just write expressions, like also here. I mean, we could write something like a formula which would take x and add y and invert it, and add 3 and invert this, and so on. But we know that at the end, we can simplify it all to a ratio of two polynomials. If we do it here, it doesn't work. So you can convince yourself that expressions, for example, like xy inverse x cannot be written as a ratio of two polynomials. Okay. You can also convince yourself that, for example, x inverse plus y inverse cannot be computed as a ratio of two polynomials in the non-commutative case. It's a nice exercise. So they are not PQ inverse for P in PQ in this non-commutative setting. Okay? So that's already a complication. We don't have some, I don't know, good canonical structure. And it just gets worse or more interesting. Suppose I give you, so in this world, you know, there's only one inversion. Even if I took an arbitrary number of divisions at the end, I will clear them out and get only one division. Where here we can look at an expression like this. So this has this nested inversion. It has two inversion of an inversion. Can it be simplified like in the commutative case? What do you think? But it's highly non-trivial. I mean, to prove, it's like the P and NP thing. Once you see it, it's one line. But actually, it can be this x inverse plus, minus, I guess, x plus y inverse. I think, yeah. Now, this is a non-trivial thing. This is called Roy's identity. And it's what stands behind the fundamental theorem of projective geometry. So it's a really useful thing also.
The example used before, like expanding inversions, like a series, sum series, or something like this. Does those trick work here?
It's a very good question. I'll talk about how to deal with this object, which I didn't really define. I'm just giving you examples. How to deal with these objects. An infinite series are one way to deal with it. Yeah.
Actually, I'm sorry, maybe it's a stupid question, but when we are talking about non-commutative algebra, are we guaranteed that always left inverse is the same as the right inverse?
Yeah.
Oh, okay.
You should check this, but yeah. Yes. So here, this is a situation where we can eliminate nested inversion, right? I mean, this doesn't have nested inversion. But if I gave you this expression, x plus, let's say, y z inverse w, so when these variables are different, and inverted it, this turns out it's highly non-trivial, has inverse height 2. And inverse height is the obvious definition, the minimal number of inversions in any expression that's equivalent. So there are lots of questions, you know, what's a canonical expression? Actually, there isn't one. You know, what's the simplest expression in some sense? Yeah.
What about also two inverses, but they're not?
No, nested. So inverse height, nested, yeah. How many times do you take inverse of inverse? Yeah. So you can write, you know, a sum of n variables like this, x1 inverse plus x2 inverse plus xn inverse is inverse height 1. Yeah. Okay. So these are some weird and peculiar things about it. I should stress that the model with division is now a stronger model than the model without division. It can do more, right? It can do more, so it's a good question, and we'll come to it whether there is division elimination if we are trying to compute a non-commutative polynomial using division. It's yeah, I mean, well, anyway, I'll tell you next time. But let's look at these more basic questions, and the first question is, what's a good object to compute? So I already alluded to the fact that I don't like these strange definitions of determinants because they are somewhat ad hoc. Another basic question is what's a natural, rational functions to compute? Rational function to compute. Can you think of any? So the answer to both questions is the same. Well, Eddie knows the answer. So people were obsessed with this. I mean, actually, for hundreds of years, and tried to define the right non-commutative determinant. And about 15 years ago, so Gelfand, I'm sure many people heard this name, a very famous Russian mathematician who worked at Rutgers the last, 20 years also. And so I think Gelfand was searching for this for a while, but the main criticism of this variant of the known variants, the many suggested variants of non-commutative determinant, is that, what does it have to do with linear algebra? I mean, determinant is so important, so powerful in the commutative setting because it, captures everything you want to do in linear algebra. You want to invert matrices, solve linear equations, and so on, right? You look at the Cayley determinant, it means nothing to solving linear equations over non-commutative variables. And if you think about it, I mean, so I'll tell you an example in a second what they define, but if you just want to solve linear equations, it's clear what you need to do. You need to invert a matrix, right? So you have a matrix X, n by n matrix, so it has variables xij. So you want to compute X inverse. If you want to solve this matrix times a vector equals another vector, you just need to invert it. What is the inverse of the? So that's a good question, but the answer is clear. It's a set of n squared rational functions. So, this should be the object we should be interested in. X inverse is a natural set of rational functions, one for every entry. And we'll talk about it in a second. I just want to say that what the definition Gelfand Retach gave to the determinant was, in the non-commutative setting, was, they called it a quasi-determinant. And the quasi-determinant of X, so it's again a set of n squared rational functions in position ij, is exactly what happens when you invert the matrix X and you look at the ji coordinate and invert it. So I'm not going to explain why it's natural. It's really natural. I mean, it had a really big impact, this definition, at least in that it turns out that lots of the known identities and facts about determinants generalize to and special determinants, when all sorts of special determinants have analogs here, and so this had an impact on lots of non-commutative fields. And also, some of these identities that were known for determinants are much easier to prove in the non-commutative case, and they immediately implies what happens in the commutative case, because if you just let these variables commute, the quasi-determinant specializes to essentially the determinant. So that's, but yeah, all of them will be the same, and they will be the determinant. You need to, yeah. But almost. I mean, you're right. It's scalar, and you need to do something to extra, but it's there. It's sitting there. Right, yeah.
It seems like Kramer rule.
Yeah, so there is, Kramer rule generalizes lots of, It's really natural, and there are beautiful papers if you want. I'll show you. But we were, I mean, as I said, even forgetting the determinant, this is clearly a natural set of rational functions, and you want to compute it, study it, and study it instead of these weird ones. But it's rational function, so you cannot study it without division. You have to have division if you have inverse in the definition, and that's some of what we did in this last paper that was just in ITCS with Pavel, Hrubes, and no, it's not. And I want to say something about this. So we looked at the complexity of computing these n-squared rational functions in the model of arithmetic circuits, non-commutative with division. And it turns out that you can do it just like, in fact, it's not surprising, you can figure it out. I'll say something about it, but we also proved the lower bound. So also for the stronger model, we have a natural function. I mean, any entry, this is true for any entry of the, you have this lower bound. So we have the more or less the analog of norms result. Here we have a 2 to the n lower bound. We don't have any nonlinear lower bounds for circuits. And so in particular, because this polynomial size, so to your question, or a problem has a polynomial size circuits and not a polynomial size formula, so also here P is different than NC. And we also have, this set of natural functions, the rational functions, is actually an analog of determinant in this sense. It's complete for formulas. So any formula can be encoded as the inverse of some matrix, and by linear projection, as before. Okay, so these are the. This is what we know. So let me just say, because I'm out of time and we'll continue next time, I just want to say, how do you invert a matrix? I mean, you think that it's, I don't know what you think, but. Well, first of all, I challenge you. It's a 5-minute exercise, but I challenge you to find the inverse of this when they are non-commutative. But you can do it. I mean, and then you get 4 rational functions that are, 4 rational expressions that are pretty simple, but they have at least, I know, monomials of length 6, some of them. So it's not particularly friendly. But the way to do this in general, is just when you can do 2 by 2, you know you can do it all. Because the nice thing about this non-commutative world is that it sort of respects partition. Let me say what I mean, and then I'll tell you why you know it. So basically, if you have now A, B, C, D, if you have any partition in which these are squares, so let's say it's all n by n, so this is k by k, and this is n minus k, n minus k. So A and D are square, right? Then you can take the algorithm, or you can take the expression you have here and just substitute these matrices, and it will give you an inverse. So it gives a recursive algorithm which you can easily implement by circuits. Yeah.
So what's the condition on A, B, C, D so that this exists?
They are generic, yeah. So I remember these are generic variables. They are all independent.
In the commutative case, you know that this exists only if the determinant is non-zero.
Yeah.
So what's the condition for?
That's a very good question.
You
Yeah.
know the inverse definition.
Yeah. Determinant. So that's a very good question, and this is what will be connected. So the question of telling whether, in some sense, in what sense a matrix is invertible, a given matrix is invertible, now not with generic variables, but with some, let's say, linear expressions or something like this, will turn out to, so which matrices are invertible. And this question, in a more concrete way, will somehow determine the fate. So here we don't know a BPP algorithm. Here we don't know if divisions can be eliminated. And also I mentioned this GCT question. They all boil down to a quantitative question about telling whether a matrix is invertible. I can state it in a...
If you ever enter the cube algorithm to compute the inverse, can't you just check if it works and see if it's invertible?
Well, you have to test identity, because how do you know when you are coming to invert that you are not inverting a zero?
No, but you compute the inverse. Then you
How do you
multiply.
compute the inverse?
You said you have a circuit.
Yeah, but the circuit computes inverses.
Oh, it has
A legal circuit is not allowed to divide by zero. So when you are inverting something in your circuit, you have to know that it's not identically zero. Telling whether it's identically zero is essentially as hard as telling whether it's invertible, because you're not supposed to invert zero. And so, yeah. So that's a very basic question. But this leads to a recursive algorithm and to a polynomial size circuit. In fact, a circuit the size of matrix multiplication to invert a matrix in the non-commutative case. I just wanted to say that what I meant, that you all know this sort of block structure, where you know it is from Strass and fast matrix multiplication algorithm. People don't, I think, stress it enough, but it's really important that in order for Strass and all the other fast algorithms to work, this 2 by 2 matrix multiplication using only 7 multiplies must work for non-commutative variables. If it only worked for commutative, which could have been the case, then the whole recursion wouldn't work. So it's really important that it works in the non-commutative case. Okay, so I think time is up, and thanks. Any questions?